But one can see the grade is so high. So you work very well, I think. So you got me, and maybe I have to make it a little bit difficult next time.
No, no, no.
Anyway, well done. So at the end of this, I will give you all to check your grade. If there is any mistake, we can discuss. Okay? So let's start the most important class, I think, classifications. Okay, so we talk about application, different classifiers, training, how we can do linear KNN, based decision, logistic regressions. Look, for example, here, one of the ideas that people that are using the deep learning is we give deep learning, we give different images. He's able to identify all the images with a right label. Look at image, the same car, if I add a little bit noise to it, it will give me almost the same car to my eyes, right? To human eyes, it's the same image. When I inject it again to the deep learning or any classifier, it will give you something totally wrong. Clear? So this is what we call it, is like we are fooling the system. Okay? So one of the solutions here, there is research going on that we need to compress your deep learning. So deep learning is a lot of parameters. So we call it is like overfitting, which I will explain later on. For example, here, difference between dogs and cakes, so you can fool the system easily, right, to generate. So you have to be careful about this challenging task that you can do. Okay, so I will start by simple idea. We have problem, how to improve it, and how to improve it again and again and again until we get a best classifier that we can do. But unfortunately, I cannot do all the classifiers. I will do only the fundamental one that give you the idea how you can progress. Okay? So let's say here we have a classification. We have different classes. So we want to learn the patterns for every class that we were able to do it in a nice way. Here, for example, we have square, green, blue, and red, and we want to see if we can do light classifications. We have the data set, we have the label, L1, L2, LQ. So here we have Q classes, okay? In the picture here we have 3 classes, okay? And we have X, so we have to every new data, we have to assign label to it, one of the classes. Can we assign input 2 classes? Yeah. If sometimes it depends on your application again. Yeah. But most likely should be not the case. Okay? So we have features. So the features are the most important. So now we are not talking about feature extractions. So we have the features and we try to do our best. Okay? But sometimes if it doesn't work, go back to feature extractions, how to do it better, feature selections, and do the classification. Or even sometimes you have to do the pre-processing, normalization, cleaning, outlier detections, and so on. Okay? Example here, we have in our data set here, we have 4 data and we want to assign to it. For example, here we have a new data here. We have 2 features, X1 and X2, or X and Y, and we want to assign to it. Is it red, blue, or green class? Clear our target, what we are looking for? We have the data, and we want to learn to get a pattern, to get a model. If there is any new data, we can classify it accurately. Okay, so this is type of applications. I will not talk about it. You can read it later on. It's almost everywhere you can do it. Some data need memory. Some data is a lot of calculations. Classifier, logistic, decision tree, random forest, SVM, neural network, deep learning, and so on. There's a lot. Okay. Okay, we want to design. So our thing is to design a classifier that involves the following steps. Who can tell me how to define your classifier when you have data? So we have to split our data to what?
Features.
To training and testing. Why we have to split the data to training and testing?
To be able to test the model.
Yeah, because otherwise I can give me the data set, I can count out very simple things. It will assign everything in the right way. If you give me new things, I will be unable to do it.
Overfitting.
Yeah, overfitting things. Okay, so we have the data. How to collect the data? We have to collect data, putting the label. And here we have to extract the features. How to do the measurement? Is it color? Is it distance? Wide? Whatever. Okay. And we assign the features to the label. And here we are constructing our data set, right? So here, feature extraction is extremely important. Even for the label, if you do it wrongly, so you are misconducting to your classifier, right? So you have to do the cleaning. And later on, we have to split this one to 3 things: training, validation, and testing. Why I split the training to training and validation? Why? I just ask you, but later on I will answer why. But just want to check if you know how I use
to tune the model.
to tune the model. But why tuning is training? Validation, we don't tune the model. What we do? To test if I need to do more tuning or not.
Yes, yes.
You see, so it's controlling the tuning. But tuning is a training. Validation is, do I need to do more, or I am either overfitting or not, or I need more. Okay? Later on, when we finish, we go to the testing data, is unseen data, and we test our model if it's working or not. So please stop me if it's not clear, okay? Okay, so we have the same thing here, data set. We do training, validation. Testing, we come out at the end with best predicted model that we want to build. Right? So if we have a new data is coming, we do the same way we extract our features, we inject it to our model, and we can do the prediction or the classification. Clear? So the data usually contains 3, as we said, testing, validations. We have to find a way how we can minimize the error of the classification based on training data set, right? And this we call it a loss function. I will explain later on. Validation, as we said, we have to test, do we need more tuning, or I am either overfitting or something is going wrong. Testing data is just to have the accuracy of things. So if you give me the accuracy of the training, I will not take it in consideration at all, right? I just look for the testing one. Okay, so this is usually, we have your data, we split it to training and testing, and do the, training, you split it again to only training and validations. Okay, or some people, they use different one, they use k-fold, cross validations. So you take, you divide it by 10 or by k-fold here, and every one you do a testing, can be the first one, second one, and the last one. But this usually we use it only when, who can tell me when? When the size of your training data is small, okay? If the data is big, better to use the first one, clear? So this is usually what we do the training, we have our data set, we do the validation, and we test all our model we have. So this is only for the training model. Sometimes when you do a lot of tuning, we are in here overfitting, right? So it's like everyone giving the right answers. Here it is the optimum one, and here is underfitting. We didn't do a lot of tuning. Or the parameter is less. For example, you have data set with 2 features, and the problem is really with 20 classes. Do you think it makes sense? So you need more features. So here we are in underfit. The optimal one, you have to be careful, okay? So here what we have, you have your input features, you do your classification. Let's say we have a binary classification, mean 2 classes. So the output can be 1 or 0. Or I can put it in 2 dimension. 1, 0, or 0, 0, 1. It's like the probability to be 1, the probability to be 2. Second class. Is it clear? Okay, so we have to label the data. Hey, a different one. If we have binary, sometimes put it 0 and 1, the output, or sometimes it's -1 and 1. I will tell you later what are the differences. It's not too much, but just to simplification only. Multi-classes, we can do it in class 1, class 2, class 3, directly like 1, 2, 3 until Q. Or we can do it with binary encoding. For example, if you have 8 classes, we do it in 3 bits, 0, 0, 0, 0, 0, 1 until 1, 1, 1, right? Binary coding. Or we can do it 1Q encoding, okay? As we did with the categorical variable, if you remember, something similar, okay? So most likely when we have multi-class, we use this one. Why we use this one is to quantify the probability for every classes, and we take the highest probability. I come back to it. So is it clear until here? One of the data set something like this. For example, here, how many features we have in your data set here? 4. And the label here is how many different classes we have? 3, according to Y1. We have 3 bits, so we have 3 classes. Okay, so L1 can be here. For example, here. This is clear, right? Just a screenshot of certain data set. Okay, feature engineering is the most important way. When you have classes, which measurement I need to do in order to disaggregate between different classes. So this is really important, okay? So it is not our course today, but it's really important, okay? Sometimes we use other transformation, sometimes we have signal, we change it to image, or image we change it to video, and we have rich features. As much as we can extract is good. Later on you can do feature selections, okay? So and it's totally another topics. Selecting the good features. So usually here we go from classes to, we call it features space. So until now we suppose the feature space is given to us. We have n features, how we can do a better job, okay? We suppose that the feature extraction was done in the medium or better way. If it's wrong way, we cannot do anything to get high accuracy classifier. Do whatever you want, is always low, right? Okay, so for example here, I give you the data here. Look, for example, here we have how many classes from the pictures?
3, 4,
5, yes? And class 2, it is not only located in one region, it can be located in different regions. You see? So when you do the classes, does not mean they are all at the same place. Can be in different places. Maybe the more the class is complex, more it has different regions. Clear? Okay? So we can say here, class 2, class 4 are a little bit complex compared to the class 1 and 3 and 5. Yes, they are collected in one single cluster. But 2 and 3 can be 2 or higher. And imagine here I give you only 2 dimensions. Sometimes the data in high dimensions. So it will be a different classes. So this is why sometimes we use GMM, Gaussian Mixture Model. You see, so different, every subclass is a model. So please, if you don't understand any keyword, let me know, I can explain more. I'm just trying to get the high level to explain the problem. Okay, we see it from the high level. Now we are going deep and deep to explain what's going on. Okay? And between the region, we have decision boundary. Okay? So the boundaries here can be a line, can be a curve, can be anything. Right? It can be smooth, it can be not. So always we try to do smooth curves is better. When there is no smooth, means we are in overfitting. You have to be careful about it. And overfitting, and also to be complex to take the decisions. If you have real-time applications, it should be easy way to take decision, yes or no, directly with 1 or 2 calculations. Okay, for example here, if you have x1 here, most likely it belongs to R3. x2 belongs to class 1, right? If you have something in the boundaries here, but the probability to have a single point in one line, the probability is 0, especially when we are in continuous cases. Remember, the probability distribution in continuous to be a single point is 0. So look, for example here, look to the pictures here. We have the data to take a dimension of 2, okay, x and y, to make it easy. I collect the data for the green, class green, class red, and yellow, and blue, right? And I try to put the histogram of it. You know how to do histogram, right? Yes. Histogram, we do it in one dimension, but we can do it in any dimension. Look, for example here, we can say, if we cut this one, cut it like this, okay? We cut it here, we get a certain curve. And the curve I projected down. Look here in the floor, the region. You see the red, the green, and so on. Those are the region of your classes. You see. But most when we are lower here, we can say that we are in the overlapping, right? If you are in the center of yellow, I am totally sure that belong to the yellow class. If I am at the top, what does mean the top? Mean go down X and Y, right? In these features, I am high probability to be in the blue one, or to be in the green one, or to be there, right? But here the problem here, the question is here, how we can estimate those histograms? We have data, how we can estimate the histogram here? So if I'm able to estimate the histogram, the problem is done, it's finished. Another thing, we can even detect the outliers. You see here, when we have something is bigger like this, and this is few things, right? Those few, we can consider them as outliers, we can remove them. So what we can do, certain threshold, we can clean the data before going to the classification. So what we do here, our target now is, you give me the input, your features, is vector of features. I have to give you the output, which class is. But to do this one, I need to calculate a functions depend on X. And this is function can be, for example, here, difference between the probability. More the probability, the green, for example, I calculate X. What is the probability that X belongs to the yellow? What is the probability of X belongs to the red? Probability to belong to the blue one. The highest one is my most likely to be this class. Clear? So you can see here G1 and G2 is like the probability of belong to this one. Clear idea here? So now the question is how we can estimate here. So what we do here, for example, we call it discriminant functions. So G1, G2, GQ, you can call it is like the probability to belongs to two things. Let me do it in 2D and we try to get the idea here. For example, I try to do two things here. This is for the blue one, and another one I do for the red one, for example, here. Okay? And I have the problem X. Look, if X is here it will be something like this, right? If X is here, yes, what will be the value of G1X and GX2? What will be the value here? So let's do 1 is the blue, this is 1, and this is 2. Look to the value of X here. This will be the G2. And then what will be? G1. Who is bigger? Which one is bigger?
G1.
G1. So if we are in this position, for sure it will be the class 1. The same thing here. If I am here, this is the value here, and this is the value. So for sure it is the blue one. So if I ask you here, what is the boundaries here? It's exactly at the intersection here. Here it will be the red class, and here it will be here the blue class. And based on the G. What is the G here is the density, the value of this one. You see the way how we can do it? Okay, so what we do, do you know what does mean this max, argmax?
Maximum.
Okay, the maximum, G1, G2, we have Q classes. The maximum, what does mean arg? Give me the index I that gives me a maximum. So this will be the class. And we put it in the label. If here, for example, the maximum at 1, here it will be 1, and here it will be L1. If the maximum at G2, it will give me 2, and it will be L2. Clear? If we have binary now, just binary, 2 classes. So what we do? Difference, G1 minus G2, and here I will take the sign. If the sign is positive, mean G1 is bigger. It will be class 1. If it's negative, it will be class minus 1. And we are done. Okay? So now the question is how we can estimate those functions. Okay? We can do another one, we call it distance. For example here, I have 3 classes, and I have I want to find a new point here, X. What we can do, we consider every class, I will summarize every class to a single mean value. So I will just consider P1, P2, and P3. So the advantage of these techniques, I don't need to memorize all the classes. Just one value is enough. And then what we do, we calculate the distance. The closest to me is my class. Okay, so the closest, the mean to X is the class we need to assign to it. Clear? So what we do here, just here, the minimum distance. By the way, here I say D. I didn't say Euclidean distance. I didn't say any type of distance. Okay? Because usually when you are in high dimensions, take it advice. Never use Euclidean distance. Never. Try to avoid it. You remember at the beginning what we did reducing the dimensions? Yeah, it would be, it give you, everything is bigger.
We will not consider the variance within the same class.
Yeah, we don't.
I remember that you mentioned another class, if the variance is small, even if it is near to...
I'm coming to it. Yeah, I'm coming to it. So here what we do, one of the techniques, the simple way, remove the class, just put the mean of it. It's more. But this is good when we, this is really nice when you do nice feature extractions and all the spaces are far to each other, so we can use the mean. We don't need to go more in complex way. Okay? If the features is done in the right way.
But doctor, there is no a good way to identify which feature is best for a class. This is just a hit and trail method, and you do just feature extraction, then classification of results are not rolled, then select another feature and do the same.
Yeah, but here you can do a feature extension features. You can extend more features. You mean if you have the data set, how we can come out with a new way of feature extraction, right?
But there is any other way to select an optimum feature extraction technique or not?
Yeah, you can, yeah, of course, yeah, you can. Or transformation, another space, a lot of techniques. So is it clear here? We can use any different classes. And you can represent any class by the mean, by the median, by the median, whatever. There's a lot of techniques in statistics that you can do it, okay? Okay, so here, let's try to do, what does mean distance here? What we do, we calculate X to the mean, yes or no? How we can write it in matrix way? X minus mean transpose times X minus the mean. Is it clear this? This is the mean distance, right? Here what we are using? Euclidean distance. If you do this one, you'll get this. Okay? Now, look at more the distance is small, I need to increase the probability to belong to it. Yes or no? So I have to get, so take G in your mind is like the probability to belong to I. Look at, if the distance is small, what I need to get? The probability is bigger. How we can come out with this one? Just take the negative one. Take minus common factor, you get this one. So this will be the probability that X belongs to I. Okay? If we have two binary, we take the two difference, G1 and G2, and here, this it looks like, I call this one W, and this one I call it W0, and this is like linear equations. What does mean here? Mean the boundaries is linear in dimension 2. We call it hyperplane. You know what I mean hyperplane? Maybe plane in dimension 3. Look, in dimension 1 is point, dot. In dimension 2 is a line. In dimension 3 is plane. In dimension 4, 5, we call it hyperplane. Okay? Just the way you can. Mesh is linear combination with the features. Okay? We have point. Okay, we have two things. But here we are considering only the mean. Can you tell me what is the boundaries here? If you have X somewhere here, look, X here, it belongs to what? P1 or P2 here? P1. P1 here. P2. So what will be the boundaries? The line, yes? Which is the perpendicular line to P1 to P2. So it will be, we take the purple. So this the blue, the blue one is the boundaries line. Okay? Anything upper to the red, anything lower to the green. Clear? But here, we did not consider how the data inside, the covariance matrix, we did not consider number points or number of data in P1 and P2. Maybe it can be unbalanced data. Okay, so, but this, I said, it is good one if your feature extraction was done in the right way. Okay? This we call it nearest centroid classifier. Okay? For example here, if G equals to -3, so do you think it belongs to class 1 or class 2? I put class 2, but do you think it's correct or not? What is G here? It's G1 minus G2, right? G1 minus G2 is negative. Which one is bigger, G1 or G2?
G2.
G2. So it should be belongs to class 2. You got the idea?
Yes.
The same thing here. Look what we did in LDA. We have two data. We find the best direction to project our data. So the two things will be projected on the line. Yes or no? So what we have here, the mean 2 is here, the mean 1 is here, and the midpoint will be my threshold. Anything in these directions is the boundary line. Anything upper is mu1, anything lower is mu2. So I'm just explaining in the rough way. We don't go in details in calculation, okay? Of course here, how we can calculate this one here, please? If I have x, if I have any x, it comes to here, right? So we calculate this distance here. So it will be w, what is w? Is the direction of the line, right? Yes? And mu1 minus mu2 over 2 is the midpoint. Yes? Look here, please. Take x here. Take x here. What is the projection here? It will be here, right? What is the value? It's this one. And I need to compare it with this point. What is this point here? It's this plus this divided by 2, which is exactly here. You got the idea? So you have x, you do the projections, and they compare this projection on the midpoint. That's all. If it's positive, what does it mean? We are in this class. If it's negative, we are in below. Exactly as we did in LDA. I just put it in classification way. Look here, you have two data here. Do you think it's better to do the projection on PCA or on LDA? So if you do the PCA, it will be these directions. If you do the LDA, it will be these directions. Of course, we have to do the LDA. LDA is constructed for classification, right? So if we do the LDA, we get those two things. So the separation will be this one. How to find the point here? Take the mean projected of the first one, of the red, the mean projected of the green one, take the average of it. We get the midpoint. Anything higher is blue, anything lower is green. Clear? Okay, so now I can do it in the right way. What is W for the LDA in binary? Is this one. S minus 1, mu1 minus mu2. What is S? Is the sum of the covariance matrix for the first one and the second one. Okay? And we do the calculations and we can do the dishes. But now, how we can improve this one here? Can we improve it better? So we are taking only the mean. Every class will take the mean, right? How we can do it better way? Look, for example, here. You have a big planet and small planet. In physics, we have the gravitation, right? Which one attracts you more? Newton law. The one that has more mass, right? So what will be here? So most likely, any point here, it will belongs to the big one, not to the small one. But the big one and small one, it is not in terms of number of data, in terms of values, how close are. Do you think here, if I ask you what is the covariance matrix, do you think it is diagonal or not? In the both scenario.
Yes.
Yes, it's diagonal, because it's circle. It is not ellipse. If it's ellipse, you answer all the question 6 in the midterm correctly, right? So when it is circle, is diagonal matrix. Okay? And diagonal are all the same or not? Because diagonal can be different numbers. What do you think? They are the same. Thank you. Okay. And here, the same. But the variance is, which one the variance is bigger, this or this? This one.
This.
Why? The range is bigger.
Yeah.
Okay, excellent. So here, if we use LDA, it will be this is the boundaries, right? Because I'm looking only the mean. So most likely, you see here, anything here, I will classify it as this class, right? But if you do in the right way, those here will be classified to the other one. It attracts more, right? Imagine here, imagine if the circle here, I put it bigger like this. It is more bigger, like this. So here it will be misclassification is big. So the LDA is not the right one, always. Okay, if you do it in the right way, by the law of the attraction, I will get this to the boundaries, the red one. So anything is attracted more. What does it mean? You see the line here? If attracted to me, it became bounded. It became like ellipse. You can see it in this way. Okay, here another thing. Do you think here, what is the covariance matrix? Is it diagonal or not?
No.
Not. It's both are. Okay. If you do the LDA, you see here. Yes, most likely this is not the right one to do. Here, for example, I have three things. Everyone is like a Gaussian distributions. So what do you think here? This is easy to classify, right? It's a little bit far from the others, right? So here it's easy. But here, between, I didn't to show, but there is a lot of overlapping, right? Clear? So everyone is like Gaussian distribution, and this equation of the Gaussian distribution in high dimension, which you can see here, please. This is the covariance matrix in the distribution. So the covariance matrix is everywhere. Okay? So it's important to do it here. Okay. Let's go now to do. Instead of using the distance to the mean, I will use Mahala Nobis distance. What is this one? Remember? We do it in the midterm again, right? Remember? So what does it mean? Here we are considering the covariance. Is it bigger or small? Yes. So what should be here? Instead of using linear, as we did before, here it will be quadratic. Why it is quadratic? We have x and x squared, okay? Because in matrix way. So we have to calculate this distance, and the minimum is the class that should be in. Clear? Okay, so what we have to do, we have to calculate. I give you x, you calculate Mahalanobis distance for the first class, for the second class, and for the last one. And we have to take the minimum. Clear the idea? Yes.
Doctor, I have a question, but regarding maybe to the other slides, the points that we need to classify.
This one?
The one before. No, the one before. Yeah, okay. I'm not sure if I'm asking the right question here, but why we need to, what if this point doesn't belong to both anyways, and it's an outlier, or, yeah, why I need to classify it either to this or this?
Ah, okay, why? Who can answer the questions? Why? For example, let me write it.
This is a new classification.
Okay. Let me just draw, so think if I understand well your questions. Now, for example, here, I have this data here. I have this one is here. And I have this point here. How we can classify to it, right? We have the mean to the mean, right? We have the distance here, and we have the distance here. Let's say here, what is the variance of, in this case, for example, let's say the variance here is 5. What is the variance here is? Roughly 1, right? Difference. You okay with that? And here, the distance, maybe I have 7, and here the distance is 2. Just roughly, right? So if you do 7 and 2, according to the first one, just consider the mean. So this point belongs to what? To the blue one, right? But if we consider the values, as we did in the midterm, what will be here? It will be here 7 squared divided by the variance here, 5 squared. And what will be 2 squared divided by 1 squared. Which one is bigger now? Which one is smallest mean?
Yeah, doctor, I understand that.
Yes.
But my question is, what if there is another class actually? This point doesn't really belong to any of us.
I mean, she says that.
Or
Isn't
there's
it
an
an
assumption
outlier?
that the word only include these two classes.
But here usually to be equal distance, there's only single point, right? Is only the red curve. So if you do the red curve, any point on the red curve, they have the same distance. But
I think she said that this is far away from both sides.
yes.
So isn't this is outlier? Why we need to
No.
Every point should be classified to each.
Okay, but let's suppose the outlier in one direction. Suppose it is right, correct one, but you have to assign to it. You have to. So here, most likely, what I can say. Let me think. Yeah, it's not. Yeah. In this case, so its point is something is like outliers, but I need to classify it.
It's a new class.
Yeah.
We need to create a new class.
Let's go to the medical field. Healthy or sick? We don't have it. How to declassify? Maybe yes. Maybe you can say is in at early stage. For example, if we are doing with Alzheimer, we can say is it early stage. So something is moving from healthier to the sick things. It can be something like this. Yeah. Yeah. Totally. I agree with you. Yeah. Or problem in facial extractions. Yeah. Yeah. Very good questions. Yeah. So it means you can define your own a new class. But this is you have to collect more data. More you are testing in the real life, you have to collect more data and you have to re-investigate your classes. Okay, so what will be here, please? Here, what we need to do now, this is our distance. The first one minus the second one. I have two classes, right? Mahalanobis distance minus things. If it's positive, it will belongs to 2. If it's negative, belongs to 1. This one here, if you simplify it, you will get it to these functions here. And this we call it quadratic equations. Just a name, because you have x squared, x, and so on, but not in matrix way, okay? This we call it quadratic. How to calculate W is here, a Q is the difference between the two covariance matrix, and this is the constant. If the two they have the same covariance matrix, here we are in the LDA. Why? Look at here. What will be Q? 0. What will be here? 0. What will be here? In the linear one, as we did before, LDA. In addition, if sigma 1 and sigma 2, they are the same and they are identity matrix, we are going to the nearest number, nearest value. You see here, we start with this one, easy. We go back to the LDA, and now we are going to the quadratic, which quadratic is like Gaussian, is much better. Okay, so this is calculations. I will not go. Look, for example, here, and this one here, this point, how to classify it, please? You have to calculate the distance, right? Distance with Mahalanobis to the mean, the same thing for the other one, and the minimum is your class. How to calculate here this one? Exactly as we did in the midterm. You do the projection on the eigenvectors. You get y1, y2. You divide it by lambda 1 and lambda 2. What is lambda 1, lambda 2? Are the variance in different axes, and you calculate the distance. Okay? So I just give you the geometric explanation about the eigenvalue and eigenvectors of it. Here the same thing. If you have a point here, what is the distance this point to the mean? You have to divide it by the values. Okay? So the same way here, I give an idea. Okay? So means the values is like your gravity to attract to it or not. Okay? So when the variance is small, mean it is tight. What does that mean tight? A small planet. It doesn't have a lot of gravity. If the variance is big, mean the planet is bigger. It has more attractions to the center. Clear? You can see it this way. Here, just small calculation. How when you do the difference here, how we can simplify to this one. Okay? I just prove how you simplify it. I won't go details on it. Okay. Here the same thing. I'm just proving it. Look, for example, here. Let's start with the easy one. Look here. I have two same shape, right? They have the same covariance matrix. Yes? They are. How to find the separations? Take the mean. What I said here, if they have the same covariance matrix, it will be simplified. It became to the linear one. What I mean here, how to find it? Take the center, and take the abnormal, the midpoint here, and this is your separation point. But if they are not here, same thing, but they are a little bit elliptic, it is not diagonal, what we do, but they are the same, you see here? They are the same. Again, we can do LDA, or projection here. We do the projection here. This is the midpoint, and we have this one. So if they have the same covariance matrix, we are in the linear one, like we are in the LDA, directly, nothing different. But if they have different covariance matrix, we are in the quadratic way. Look, for example here, you have two data, A and B, yes? They have the same size, okay, same number, same size. I have this point here. What do you think this point belongs to the class B or the class A? But if you answer, you have to justify, of course. So I have the data here, and I have the data here, and I have the point here, right? How to classify this one, please? Okay. I take the distance to the mean, right? What is the Mahalanobis distance, please? Let's say here, here lambda 1 is, for example, 10. This is 10. Lambda 2, for example, is 1, right? What is here, please? Lambda 1 can be 1, and lambda 2 can be 10. Okay, same thing, just I'm rotating, right? What will be the distance here? This distance here, the distance here, I have to divide it by lambda 1, by 1, right? Yes, here, again. The distance here, what will be here, please? This distance plus this distance, right? Yes or no? What will be distance here? Here is same thing like D, the same D, and this is like, call it D2. So what will be the distance here? D2 divided by 1 plus square, sorry, square, and here plus D square divided by 10, right? Which one is bigger, please? So for sure it belongs to the B, right? It's more clever to you.
Actually,
Yes.
for one data, we divided by lambda 1, and for another, by lambda 2.
Yes. Okay. This one I have to compare it with what? With D square over 1, right?
Yes.
Yes.
So the another one.
Okay. Let's say for example D is 2, right? This is 2, and D3 we take it as 5. Yes. What will be here, please? What will be the distance here, please? It will be 5 plus 4 out of 10, roughly, yeah? And the other one is 4. Which one is smaller? It belongs to B. It's clear, right? Is it clear?
Yes, sir.
Yes.
If I do it another way, would it be right? Like, if I do the SVD, if I do the straight line here, like project the data, like.
Hey, well, I'm not doing with LDA, yeah? No, here we are doing in the quadratic one. Mahalanobis distance.
Isn't it? It's going to be the same answer as well.
Sorry?
It's going to be the same answer as well if we do it by another way.
No. Here, maybe in these specific cases.
Yes.
I can come to the second question, yeah.
But that LDA will not separate the two classes.
SVD.
For example, here, what should be here LDA here? What should be the direction of LDA, please? I ask a new question here. What should be LDA? In which direction you need to do your projections in order to minimize the variance of the projection, and the mean should be, the two means should be far to each other, right?
The same, I think.
Present?
Yes, present.
Present?
For example, here, if you do this one, it will be fully the same mean.
Yeah.
So for sure, here, this one here, the mean is here, and the mean is here, right? But the variance of this one is too big, right? The variance one is perfect, it's small, the direction is good, but only the variance of this one is a little bigger. Can we make it a little bit oblique like this? But it will be overlapping. So most likely, I'm not sure, but most likely I think it's this one. Okay? So what will be the separation? It will be this is your separation. Okay, let me give another one to make it more clear. Here, this point here. It belongs to what? To A or to B, please? Use the same thing here, please. Use the same idea here. 110 and 110. Here 110 and here 10. Yeah. What do you think? Look here. This is me, right? This distance here, I have to divide it by 10. And this distance here, I have to divide it by 1. Just do it after we go to the prayer. So this one here, we divide it by 10, and this one we divide it by 1. So which one is smaller, please? B or A? B, exactly. Yeah. So look here, to the point here, the variance here is bigger. It can attract more. But the variance here is small, it will attract a little bit less. Right? So what does it mean here? If I want to do, look here, if I want to do here, by Mahalan of this distance, it will be, this is separation. You see here? This is separation. And anything here which will be misclassified, of course. Okay? But anything here, it will be attract more to this one. So this is the separations. Okay? Yes?
I'm not sure if we have a point very near to the A.
For example, here? Here, right?
Yeah.
Okay, here, yes, it will belongs to, let me think. Okay, let's do it here. Very small to be. It should be x divided by 1, and the other one which will be the x plus something b, d divided by 10. And have to take the minimum. 1 versus 1, right? Here, if x, for example, take x 0.1, very, very close, right? Here, which will be 0.1, and here, let's take, for example, this is 5. It will be 5.1 over 10. Yeah, it will belongs to A. So maybe this one, yeah, maybe I didn't do it the right way. Let me do it another one. Something like this, yes. Or, no, you are right, maybe something like this, yeah. Because anything here, it will be, yeah, something like this. But sometimes it's difficult to guess. You have to write it. Okay, let's stop here after we go to the KNN, please. But please, just 10 minutes, no more, in order to finish all technical details. Okay? Now you are smart student, right? You can do good here. So, yeah, see you in a few minutes.